But just want to remind you of what we did yesterday. So we talked about states in particle theory. We said that matter is anything that has mass, which means it's made up of particles, and it has volume, so it takes up space. And then we said there are changes of state. The physical change would mean that in every single situation you have the exact same chemical, we've just spread it out a little bit. So we have it nice tightly packed if it's a solid, very little space between. When we go to a liquid, it's because we've given them a little bit more energy, so they're bouncing around because all particles are moving all the time. And so it's able to spread out a little bit more and they can move past each other. And then when you really spread them out because you've given them lots of heat, then they become a gas. And if you remove heat, you can go back in the other direction. So we have melting, we have evaporation, we have condensation, we have freezing. And then we also said that we can go from a solid all the way to a gas. We can skip the liquid phase. And if you do that, it's called sublimation, or you can say that something has sublimated. And then from a gas to straight to a solid, skipping the liquid stage, deposition, or we could say it deposited. Remember as well, the melting point and the freezing point is the exact same temperature. It's just the point where either I'm about to melt or I'm about to freeze. And it's that tipping point that you have where if you just add ever so slightly a tiny bit of energy, you're going to go from solid to liquid. If you remove a tiny bit of energy at that exact temperature, you're going to go from liquid to solid. You're going to melt a little bit or you're going to freeze a little bit, just depending on which direction you're either adding or removing that heat. Same thing with boiling point, condensing point. It's the exact same temperature. Either you're going from a liquid to a gas because you've added a bit of energy, or you're going from a gas to a liquid because you've removed a little bit of energy. Some of the questions that you might see might say, I'm just going to make up a substance. Substance X has a melting point of 300 degrees Celsius. So it's got a melting point of 300 degrees Celsius. And then I say, what state of matter will it be if it's at 400 degrees Celsius? And you would have to know the boiling point as well, but you could guess and you could say, well, at anything 300 degrees and under would be solid. So if it was over 300, even if it was just 301 degrees, it's probably a liquid. Now you'd have to know what the boiling point was as well. So let's make it easy. Let's say that it's at 300 for the melting and it's at 500 for the boiling point. So at 500 degrees, it turns into a gas. So it takes 300 degrees to melt it and it takes 500 degrees to make it a gas. So anywhere between 300 and 500, you should have a liquid. Anything less than 300, you should have a solid. And any temperature higher than 500, it should be as a gas. So those are the types of questions I might throw at you, and you'll have to remember what melting point and boiling point means. And then it means that you're in between liquid and gas or in between solid and liquid. Then we also said it's important for you to know the particle theory of matter. Remember that it describes how things are put together, its structure, and how it behaves, how the matter actually behaves. So how those particles are going to behave is important here. Particle theory. Please memorize these 4 things. All matter is composed of very tiny particles. We're going to call them atoms and molecules. All particles have space between them, so they're not actually touching one another. They have space. All particles are always in motion, and all particles in the substance are attracted to each other. And it's this attraction thing that allows things to stick together. So if you have particles very close together, they are very attracted and they stay together as a solid. If you pull them apart a little bit because you gave them too much energy and they move too far away from each other, then you have a little less weak and then they'll flow over each other like a liquid. And if they're very far apart, then you've got a gas because there's a very weak attraction. And that's the basic idea. So that's how we talk about strong forces, weak forces, holding together different substances, and explains why we have the different states of matter. So welcome now to your lesson for today on classification of matter. Classifying matter is not difficult to do, but sometimes people get a little bit confused. So I'll try to walk you through it and make it easy for you. So all matter is made up of different types of particles. Now we can have a single type of particle, or we can have a combination of different types of particles stuck together. And that's the basis of what we're talking about today. What are the different types and combinations of particles that we have? Okay, and this is directly from particle theory. All matter is made up of particles. Each type of matter is classified by what we call properties, and these properties are very distinct. When we say distinct, we mean unique or very recognizable for certain types of elements. And they have both physical and chemical properties. So for example, pure iron is actually silver in color. It's very hard. That's why we can use it in our hammers and whatnot. We can use it to try to make another type of metal called steel, and also reacts with oxygen to form rust. So just looking at its basic properties, what it looks like, silver colored and hard, those are physical properties because those are describing what it looks like right now as it's sitting there as a lump in front of me. If I mention the word reacts and I tell you what it's reacting with and that it's forming something else, a different compound, this is how it behaves during a chemical reaction. So we would say this is its chemical property. So its physical property, well, it's just sitting there as a lump right now. And then its chemical property is what it would be when it's actually changing as a chemical. How does it react and form new compounds with other substances? Pure gold as well. If you were to look at pure gold, it's actually yellow, as you know, but it's actually a soft metal. It's not a hard metal. You'd be able to make a dent in it. It's quite soft. You can, and the other thing is it does not react with oxygen. That means that while iron will actually rust, gold never will. It's one of the reasons why we love to use gold for jewelry, because it's soft, it's easy to bend, and it's not going to tarnish. It's like the way silver would. Silver goes kind of like this blackish color, and iron goes the ruddy rust color, the red color. But gold never rusts, which is why it's so valuable, okay? And because it's a bit rare. So let's jump then into the categories of classification of matter. Let me show you this graphic here. So all matter can be broken up into these two major categories. A pure substance, which means that everything in the pile is identical. Every single particle is exactly the same, or a mixture of those particles, of different types of particles. Within the pure substance, we have things called elements. You're going to learn about the periodic table this year. We're going to learn about all the naturally occurring and man-made elements that we can find so far in the universe. And you'll memorize a whole bunch of them, know their names. You probably already know some of their names. Iron is one of them. Gold is one of them. And these are, everything in there is just a single type of atom. And again, we'll learn about atoms as well in a different lesson. A compound is when you take those separate elements and you stick them together in a way that they're actually going to share electrons, so that they don't actually behave like the individual elements anymore. Now they behave like a completely different set of particles, a different thing. So we call that a compound. They've been put together and they have totally new properties. On the other side of it, when we mix things, these mixtures, even though a compound looks like it's a mixture of elements, it's not. A compound is chemically joined so that they become one unit, and neither of those atoms anymore will behave like the original elements that they came from. They behave totally differently. So let me give you a quick example. You have hydrogen, which is a gas. It's an explosive gas. We're going to make some hydrogen in a lab, and you're going to light it on fire, and you get a little mini explosion in the lab. It's quite fun. Makes a huge popping noise. It actually rings your ears a little bit. And then you've got oxygen, which is also a clear, colorless gas. You can't see it. And it's very flammable. It's literally the one thing that fire needs to burn. So you're going to take two different elements. You're going to take hydrogen, which is an explosive, invisible gas. You're going to take oxygen, which is a flammable, invisible gas. And when you put those two together, you end up with water, which is obviously not a gas. It's now a liquid. And instead of starting fires, it puts out fires. Lots of different properties that'll be different. So a compound, when you join the elements just right, has its own completely unique set of properties. Water is very different than the hydrogen and oxygen that it was made from. So we would say that that is a compound. And we would say that because every water molecule behaves like every other water molecule, it's a compound, therefore it's a pure substance. You have a pile of water, not a pile of hydrogen plus oxygen sitting there. A mixture is different. When you have a mixture, you don't actually join those atoms together. So here we've got something called a homogeneous mixture, where we have this looks like an element to me. This is a single atom next to a compound. These guys here, you can see the yellow and the green, they're not joined to one another. They're just sitting next to each other. In fact, there's even space in between them. So we would say that this is a mixture. Same with this one over here. Here we've got water and some other compounds sitting here. And they are not actually joined to one another. They're just sitting next to each other. So we have mixtures of pure substances. If it's a homogeneous mixture, then we would say that it looks the same when I look at it. I can't tell the difference because right here we're zooming in on the atomic scale, but if I was to zoom back out and take a look at it, I can't tell the difference between just regular water and if I put salt in it. It doesn't look any different to me. So you can have a pure water look exactly like a mixture of water, and in that case we would say it's a homogeneous mixture because it looks the same to your eyes, right? If it's a heterogeneous mixture, you can see the difference. You can tell because they don't completely mix together like that, and you can see that one part is maybe looks brown and the other part looks clear. Whatever it is, you can tell. Okay. We have other names beyond just the homogeneous and heterogeneous. If it's a homogeneous mixture, then we say that it is a solution. So again, salt water would be a solution. If you get instant coffee and you put it into hot water, you can't tell the difference between the coffee and the water anymore, so it's a solution. Okay? With heterogeneous mixtures, we have two types. We have a mechanical mixture, and we have something called a suspension. Think of mechanical mixture in terms of things like if you had a bunch of nuts and bolts in a jar, you'd be able to tell the difference between the nuts and the bolts. Or let's say you had some kind of a cereal, like a Lucky Charms cereal. You can tell the difference between the different types of Lucky Charms. You can see that difference. So that's heterogeneous, and it's a mechanical mixture because I can separate it pretty easily. A suspension, an example of that would be things like salad dressing, where you've got a whole bunch of herbs kind of floating around in the oil, and you can see the difference, and you can see that they're just kind of floating there, that you can see one part is oil, and you can see one part is different types of herbs. So there's your hetero, I can see the difference, mixture. So that's it in a nutshell. Let's go through now and talk about the actual details. So again, pure substances are made up of only one kind of matter in the entire pile, and that matter has unique physical and chemical properties. We'll get into those in our next little section here. The smallest, tiniest particle that you can find is a piece of an element, and we call those pieces of elements atoms. Again, we'll talk about structure of atoms in a different lesson. When you have a compound, you have a compound that is composed of molecules. So an element is made up of atoms, and when you chemically join the atoms together, you end up with molecules, or we also talk about ionic crystals, but that's too advanced for this lesson. Okay, so elements are made up of atoms, compounds are made up of molecules. So you can have your example here, gold. Well, that's an element, that's right off the periodic table. Oxygen, carbon, aluminum, hydrogen, all of these are examples of elements that you can find on the periodic table. Okay. There are three main types of elements. You have metals. You're familiar with a lot of the metals that you've seen. I'm pretty sure I could put a bar of metal in front of you and you probably know that that was a metal. They usually tend to be shiny silver colors, but they're not all. Copper can be an orangey color, and other ones you haven't even seen yet. Most of the elements that we have are metals. Then you get these weird ones in between. They're called metalloids. Metalloids are called metal-like. That's what metalloid means, because they behave a little bit like a metal, but they also behave a lot like something called a non-metal. Non-metal, there's not as many on the periodic table as the metals, but non-metals, they're kind of brittle. Sometimes they're brightly colored. Sometimes they're even a gas. They're not even a solid at room temperature and things like that. But we'll get into all those properties of metals, metalloids, and non-metals in one of your future lessons. This is a little bit advanced, so it's okay if this particular information doesn't stick. But some elements are considered monoatomic. Mono means one. It means that in normal life, when you look for helium gas, you get helium gas put into birthday balloons so that it will float. When you have helium gas in those balloons, it's just little individual helium atoms that like to float around by themselves. They don't like to connect to anybody else. They just like to sit there by themselves. So that would be considered monoatomic. This type of element just likes to be by itself. But there are some elements, and you'll learn more about this in grade 10, some elements are called diatomic. Di meaning two. So this is when this particular type of element, specifically hydrogen gas, in this particular example, it actually likes to stick to itself. So two atoms of the same element get bonded together, and we would just say that this is a diatomic element. Even though there's two atoms there, technically, we would still say, because they're both hydrogen, it's just the way hydrogen likes to hang out with itself. So we say diatomic element instead. This is a really important piece of information going forward. It's going to make more sense when we get into the actual structure of the atoms in your future lessons, but I'm going to put it here again for completeness of the note so that when you come back and study, you've got the full idea of what's going on. But if you want to form a chemical bond between atoms, so you want to make a compound, and you want to get two different types of atoms and put them together. So like in this picture here, we've got these white atoms, and then we've got these black atoms here. If you want to actually get them to stay together so that they don't just sit next to each other, but they actually join, then you have to do something funky with their electrons. And we'll get into electrons in a little bit. Now, either they're going to transfer those electrons. So let's say the guys on the outside, the black guys here, let's say that they gave up an electron, and then these guys in the middle here, they stole an electron. That's going to make sure that these guys who stole the electron are forever holding on to it, and these guys who lost their electron are forever chasing it and they want it back. So you're going to see that they have electrons in common, and that's what we'd say transfer. There are other types of molecules that are going to form where they don't necessarily one steal them and then they're forever chasing, but rather it's more like a custody agreement. They end up sharing the electrons. So sometimes the electrons spend some time around the white, sometimes they spend some time around the black, and it's more of a shared agreement between them. Either way, it's the electrons that they have in common, and they are going to be called bonded together because they now have a reason to stick together. They want those electrons, right? Everybody wants to keep their electrons. So they're going to have them together, and they're going to be joined chemically. That's what we say is it. Now it's now chemically joined. It's chemically bonded. We've had a chemical change when these two guys got stuck together, right? And again, that'll make more sense after we study the structure of atoms. So a compound then is made from two or more atoms that get joined together chemically. Again, they have electrons in common. So they are going to form molecules. So an element is made up of different types of atoms. So one element has one type of atom. A different element will have a different type of atom. And then a compound is when you join these guys together, these atoms together, and you make molecules. Every molecule of water has the same physical and chemical properties. That's really key. That's what makes it a pure substance, because it has one set of properties. Every molecule of water anywhere in the universe behaves exactly the same as any other water molecule anywhere in the universe. So it's a pure substance. Here's another picture here to try to help explain the electron idea. So water, H2O, is a compound. It contains the elements hydrogen and oxygen, like I mentioned before. You have two hydrogen atoms. That's why there's a little 2 beside the H. And you have one oxygen atom. There's no number for the oxygen because we tend to drop off ones. We kind of just ignore ones a lot in math and science. So if you see the big O, you already know there's one sitting there. You only need to tell anybody and give them a number if there's more than one sitting there. So two hydrogen atoms with one oxygen atom in every molecule. And this is roughly how they're kind of laid out, kind of like a Mickey Mouse ears. And if you were to zoom in and actually look at the structure of not just a big circle here, but actually look at how it's built, you'll see there's a little, what we call a nucleus in the center here. And that's got a whole bunch of positive charges in the center. And then you've got these blue things are little negative electrons around the outside. And you can see that hydrogen, the little single one here, these are very small atoms compared to the big oxygen atom. And they are sharing these electrons here that they have in common. This is why they want to stick together, because hydrogen would like to have 2 electrons around it, but it only starts with 1, so it's going to borrow oxygen's electron. And oxygen would like to have 8 around it, but it only starts with 6, so it's going to borrow 1 electron from this hydrogen and 1 electron from that hydrogen. So it's going to stick together electrons in common. Table salt, which is sodium and chlorine, Na is sodium, Cl is chlorine, is a compound. So we know that they're chemically joined atoms. They have electrons in common, and they have those 2 elements there. This one is actually a very interesting combination because sodium is actually a metal. It's a very soft metal, and that metal you can actually cut it with a butter knife because it's softer than steel, and it's very explosive. It's quite fun. We're going to throw it in some water, and you're going to see it burst into flame. It's a metal that bursts into flame on contact with water. So cool. Chlorine is a toxic gas. They used chlorine gas when they were doing trench warfare during the World Wars. If you've heard of mustard gas before, that's pretty much chlorine gas. It's very toxic. If you sniffed it in, it would burn the lining of your respiratory system. It would probably kill you if you burnt it badly enough. So you have this explosive metal, that shiny silver solid that bursts into flame when you throw it in water. You have this toxic gas, but when you chemically join them together and they end up having electrons in common, they don't behave like their original parts. In fact, putting these guys together is very delicious, because once you make this little compound here, you end up with table salt. We use table salt to make food taste better. We use it to preserve foods if we want it to last a longer time, so on and so forth. Like, it's such a useful, wonderful compound made of two very dangerous elements, but once they're together, they no longer behave like either part that they came from. And that, again, is why we call compounds pure substances. They have brand new properties. They behave differently than they ever would have if they were broken apart again. So pure substances, you have elements and you have compounds. If it's a compound, it's different types of atoms with electrons in common, and they act as one unit. So we say that that is a pure substance. This is pure salt right here. So now let's chat about mixtures. What the heck are mixtures? Well, mixtures are just when you take these different things, these, you can see here there's two different types of compounds here, and you don't join this compound to that compound. You leave them as separate compounds. They even have space between them. They will be sitting next to each other, and so you have what you call a mixture. It's a combination of pure substances, a whole bunch of different pure substances in a pile. What's different about a mixture and a pure substance is that mixtures you can separate again quite easily through physical means. You don't need to mess with any chemicals to try to, we're not trying to break apart this molecule. All we have to do is move this molecule away from that molecule. And so we get our two different types of mixtures then. We get the heterogeneous mixtures, which are the mixtures where you can see the different substances. Again, hetero meaning different. And these are usually, again, able to be separated physically. So what do we mean? What are examples of separating physically? Well, let's say you've got a bunch of sand in some water and you just want to get the sand out. Well, you could just filter it out. You could pour the sand and salt and water or whatever it is. You could pour it through a filter and you'd be able to reclaim the sand. The water would be separate now and the sand would be separate now. In some cases, you can actually just let them sit there and they'll separate on their own for heterogeneous mixtures. So something like a salad dressing. Before you go and pour it on your salad, you're going to have to shake that thing up to make sure that the herbs haven't just sat all at the bottom. You don't want to just pour out oil, which has floated, up to the top because it's less dense. So it just depends on the type of mixture. Sometimes they will separate on their own. Sometimes you have to do the work of separating them. So again, we have our two types of heterogeneous mixtures. We have a mechanical mixture, where you get different substances that you can see. So a chocolate chip cookie, soil, you can see different parts of soil, like the rocks or whatever that's built into the sandy stuff that's in the soil. Mixture of salt and pepper, you can definitely see the difference there. That's a mechanical mixture. A suspension is when one thing is floating in the other. So that would be the salad dressing is the best example of that. A homogeneous mixture, it was when all the parts look exactly the same. Every single part looks the same. So homo means same. Solution then is what we would call a homogeneous mixture for our course. It looks like a pure substance, but it's not. It's going to have different things floating in it. So again, sugar would be a pure substance, water would be a pure substance, and when you put them together, you get a mixture of those two different substances. And we would say that one substance has been dissolved in another. So up here, suspension, I can still see the differences. I would say one is suspended in the other, but down here where I can't see the difference, I would say it has been dissolved because I can no longer see the actual separate sugar particles. But it's just a mixture. They haven't chemically joined. I haven't shared any electrons between the sugar and the water. And so because of that, I should be able to separate the sugar and the water pretty easily by physical means.